we have the next part of the session is by Tianlong, who will tell us about competitive dynamics of visual markets with choice.
Thanks for introduction. And so my name is Tianlong. I'm from Columbia University. And today I'll talk about our work on the tentonium dynamic for Fisher market with Charles. And this is a joint work with Pascal Chaudhry, Christian Kerr, and Ruta Mehta. So, okay. Thanks for the first speaker. I guess I don't need much introduction to the basic concept. So I'll give a quick overview of the Charles Fisher market. So this work will focus on the Charles part. So in Charles Fisher market, we have a set of agents and a set of Charles, right? So the agent is taking Charles to earn some money. And the agent will incur some disutility for the Charles assigned to her, and she has a earning requirement to meet. And the Charles, we assume it to be divisible and has a utility united supply without loss of generality, and the price can be interpreted as the price per unit of the Charles done by the agents. Right? And the target is a competitive equilibrium. Right? It's a very classic, and so it's defined by a pair of price and allocation, such as so each agent will get this utility minimizing Charles bundle subject to the earning requirement, and each Charles will be complicated allocated. So in this paper, we'll consider general continuous convex or homogeneous disutility functions that are we will, like for the ideal presentation, we'll assume that those disutility is strictly increasing in each coordinate. While in many results of the paper, this assumption actually is stronger than necessary, and it can be replaced by some weaker assumptions like local non-citation. And the main class of most interesting class of utility is the disutility functions. We define as a convex CES disutility of this form. And this is kind of a mirror the CES disutility in good case. Right? And the full spectrum you can see is defined by rho from 1 to infinity. And the rho equal to 1 case is the substitute case. And when the rho goes to infinity, it turns to the complementary case. So we'll start from the very directly dynamic. So we see the very directly analogous tentonium dynamic just mirror the good case, right? So in the good case, right, if you want goods to be more attractive, you need to increase the price. Oh, sorry. So if you want the goods to be more attractive, you need to decrease the price. And in contrast, in the Charles case, if you want to make a Charles more attractive, you need to increase the payment, right? So intuitively, you need to more direct, very direct way to get some tentonium dynamic is just flip the sign behind the extra excess demand. Also, so by the way, so the tentonium dynamics, I'll give some background. So you just adjust the price based on the excess demand. So in good case, it will be if the excess demand is positive, you want to increase the price, and in Charles' case, that would be the opposite direction. So this would be a very kind of naive tentonium, I would just call them like that name. And we know that in the good case, the tentonium is very powerful, and it's converging very well the range of the utilities. While in the Charles case, it's doesn't work, and it's kind of known in previous papers, but I don't know what they really formally studied it, I guess. So why is this the case? So here I go observation, and I believe it delivers some kind of insights on this problem. So different from the good case, the excess demand is just the demand from the agent minus the supply, right? And has some conflict effect. So if you look at the good case, right, for some goods, if the price of the goods increase, then on the one hand, the good will become less attractive because it's more expensive, right? And the demand will tend to be decreased. And on the other hand, because the per unit price increases, so giving the same amount of money, the demand will also decrease. So it's kind of the two forces in the same direction, right? And in this case, you will say, oh, there's a larger demand than the supply, so you can just say, oh, the price is too high, and I want to decrease the price. While in the Charles case, it's not the case. So for Charles, if the price increase, so actually the Charles will become more attractive, and the demand should be increased. On the other hand, if the price is increase, the per unit price is also increase. So giving the same amount of money, the demand will decrease. So it's kind of saying the change of price will bring some conflict effects to the excess demand. And in turn, so if you say, oh, the excess demand is less than supply, so it's very hard to determine whether the price should increase or decrease. And formally in this paper, we show that so for the general convex CES, Charles Fisher market, for every that market, for every disutility, you can construct a counterexample such as coupled with any hyperparameters. You can the naive Charles tentanglement will diverge from an unique competitive equilibrium. So it's kind of robustly diverge. So what we do in this paper is we proposed an alternative tentanglement dynamic with very mild and interpretable modification, and we call it the relative tentanglement. So what we do here is as follows. So if you still remember the naive tentanglement is just the first line and the third line, right? So, but here, what we do is we pick excess demand, the ZT there, and we just subtract the mean of the excess demand over all the Charles, and we use that. We call it relative excess demand to give us some signal to the price to indicate whether it should be increased or decreased. So essentially, we are using relative excess demand compared to the averaging level. And the good part of this is by doing so, we can the price level can be maintained in a constant level. So in particular, we said it's the sum of the price has to be the sum of the budgets. And we denoted this price subspace as HB, and it will be used later. So the way we show the convergence is so we utilize the function showed up in the Charles EG2 program, which also studied by the first speaker's work. So here so he didn't talk much about that. So I guess I'd better to give more background of this program. So here I just present the general version for the any CCH disutilities. So the inner log part, is the defined like indirect disutility functions, which also mentioned by their paper. And So this program, before this, we know the linear case, right? And so this is a generalization to the general CCH DC utilities. And we focus on the restriction of the function f to the price subspace, we just defined before, and we regard that as a potential function of this problem. So this kind of makes some connection between the subgradient dynamic system, you can think of some first order things, and associated with that unconstrained optimization problem. Well, this potential function itself is still a non-convex and non-smooth, and so in that case, the chain root sometimes doesn't even can fail. So we still need to some additional properties. So even, for example, it's even hard, even you need some additional property to compute the gradient of this function. So it turns out that this function, even it's a non-convex, non-smooth, it has some, it is subdifferentially regular, which is very nice in terms of the first order optimization. And it's very useful to prove the equivalence between and the convergence to choice C. So by utilizing this tool, we prove the continuous version of the relative time tournament can converge pointwise to a stationary point of the point potential function, which is corresponding to the competitive equilibrium. And the next step, so the discrete time variance can be seen as approximation of the continuous time counterpart. And by doing that, we can figure out by setting some proper step sets, the convergence of discrete time relative time tournament can also be shown. So the bold proof will also lead to an optimal program for general CCH disutilities. And this program is of more general interesting to develop more optimization algorithm. And this program also proposed by the Wei Qiang, the first speaker's paper. Okay, so the next part will focus on the convex CES disutilities. So in that case, we look at the iteration complexity to compute an epsilon approximation CE, and it turns out that you can have some 1 over epsilon square convergence rate guarantee for that. The main challenge would be sometimes even the price vector. Even the price vector can be very close to the stationary point. The excess demand signal can be very strong, so it's very hard to detect where's the stationary point. And to handle that, that's directly connected to the smoothness of the potential function, and essentially that will depend on the inner log part, which is gauge dual, also called the gauge dual of the disutility functions. And I'll just deliver some nice geometric interpretation and for this. So you can see if you look at the unit level set, when the boundary is more flat, it would means that the dual function is more non-smooth. So the result is that we include the linear disutility and the anti-NF disutility, and without that, in the full spectrum of the CES disutilities, we can show the 1 over epsilon square root convergence rate. So I'll skip this part and mention I think very interesting application of the Tianlong dynamic is can be we can use that to study the stability of the CE. That's if you if the perturbations, oh, okay, so stability, and we can show some interesting results, like you can characterize the stability of the individual CE based on some combinatorial structures, and also the well-known maximum of natural welfare compared to equilibrium can be shown as always stable, like locally stable. Oh.
Any questions? We're still in the range of efficient markets, and in comparison to the previous or the next one. Okay.